Hello, and welcome to Team Cartographer's submission to the 2022 NASA App Development Challenge. We use Python to visualize latitude, longitude, elevation, slope, azimuth, and more in our app, which has toggleable features, and we'll take you through our process, our code, and what we could have improved for our next one throughout this video. We hope you enjoy. Our team was mostly successful when meeting most of the criteria for the challenge. However, our hardest part was getting the communication checkpoints, and we were only moderately successful with getting that set up, as our algorithms proved to be too inefficient at times, or also just were outright way too difficult to implement.
Upon installing and unzipping the app from our GitHub page, you will be led to all the app files. Here you will run pathfinder.exe, which will let you upload longitude, latitude, height, and slope files. Additionally, you will also be uploading the distance between points. This will let our data processor program and every other program run based on the site data from these files. Once you submit the pathing, then you'll see the ADC lander app eventually pop up on your homepage. This holds all of the data for the app. In the raw data folder, you will see the paths to data, which is the output from the pathfinder.exe file. In process data, you'll see all of our data processed to set it up for the visualizations. Our last folder is app files. Within app files, we contain all the rest of the data related to the app, including the height maps, runner data, and display.exe. Display is our main file that runs the entire app overall. Upon launching display, you will be introduced to the entire app environment, which displays latitude, longitude, height, slope, azimuth, and elevation. You can also see the key bindings at the bottom of the screen. Here we have access to the height map visualization, which is displayed right now, the realistic moon, which you saw previously, the slope map, which is right here, our non-textured moon, which is built for increased frames per second, and the path, which was selected by the A-star algorithm. Each of the communication checkpoints was selected based on good temperatures, but also based on interesting sites such as different elevations, craters, and more that might be of use for studying. Additionally, we have a 3D feature within our app, which lets you see the surface in 3D with all the same toggleable features, but gives you a bird's eye view perspective of everything in our regional site.
One of the largest drawbacks of our initial design was inefficiency. The first draft of the initial data processor code was not optimized at all. Our initial design used Unity as selected by decision matrix. However, Unity was not as user-friendly as we would have hoped. When an alternate engine called Ursina came to our attention, we stopped and reevaluated our decision on which engine we would use. After rescoring the decision matrix, we found in theory and in practice that Ursina was much better for our purposes.
The idea first came when two of our team members found out about this competition online. From there, they started recruiting other interested and dedicated students to join and formed our current team. We all joined for similar reasons. Firstly, all of us were interested in working on a project for NASA. Additionally, some of us were interested in the programming or developmental aspect of this challenge, while others were interested in the more scientific aspects of this challenge.
One of our biggest learning experiences throughout this challenge was the sheer amount of code that we wrote. We all had taken computer science classes in the past, however, this was our main venture into applying it in such a grand scale. Our algorithms, our file setups, our calculations, and everything were just a great learning experience to try and figure out how we can apply all that we have learned in computer science classes, such as methods, loops, etc., to a practical setting.
We approached this challenge by splitting into two teams based on different strengths and interests. The development team and the science team. Both teams focused on various aspects of self-studying and learning material that isn't traditionally taught in a classroom setting to apply to this challenge.
So what led us to our final design and approach? For the most part, we tried to look at the different landing sites which the rocket may land by analyzing maybe how much water would be in that area or how much light that area would receive. Talking to our NASA mentor, and just with all those little things to make sure that we could have a holistic outlook on what we were doing.
A second-year computer science student at UPenn introduced us to Dijkstra as an alternative to A-star for pathfinding, and this really helped us understand that we need to have a decision matrix to sort of weigh our priorities when running Dijkstra as a pathfinding algorithm. Then a first-year CS student at the University of California, Riverside introduced us to hierarchical pathfinding for A-star called HPA-star, along with how to make textures better and how to use quad trees to decrease the runtime of Dijkstra. Finally, Professor Tolstenko of the University of Champlain introduced to us quad trees, and more specifically spatial hashing on how to decrease the runtime for our rendering with Dijkstra, as well as caching data offline before running Dijkstra, as well which also help decrease runtime.
In terms of community engagement, we were very active with our outreach. We held presentations at local middle schools talking about the challenge and our process throughout the challenge, inspiring their students to participate in the middle school levels of the ADC in future years. Alongside that, we taught them about algorithms, 3D modeling, and how to get started with coding if they would like to pursue that in the future. We also led presentations in conjunction with our school's computer science club, alongside teaching them a specific side of Python, which is visualizations and 3D modeling. We also update our social media pages, albeit less frequently than we would have hoped, showing our progress with algorithms, runtimes, and basically the model in general. Our largest change to make in the future is streamlining the file creation process, as well as improving our pathfinding algorithms. However, we didn't implement them in the best way possible. We'd also want to research more about different potential landing sites, as we feel that was prioritized a bit less than it could have been. And we want to improve the app UI as much as we can, possibly improving the mesh, adding more details, or more. Thank you for your consideration and your time in watching this video, and we truly hope you enjoy.